A capacitance C charge, a capacitor C, a capacitor of capacitance C charged to a potential difference V is discharged by a by connecting its plate through a resistance R. Find the heat dissipated in one time constant after the connections are made. Do this by calculating integration I square R dt and also by finding the decrease in energy stored in the capacitor. Solution: we have dh equals to I square R dt, or R equals to I is given by I naught square e to the power minus 2 into t by tau dt equals to R into V square by R square e to the power minus 2 into t by tau dt, or V square by R, because R will cancel, e to the power minus 2 into t by tau dt. Hence integrating, the heat will be 0 to tau dh, or 0 to tau V square by R e to the power minus 2 into t by tau dt, or V square by R integration of e to the power minus t tau by dt will be equal to e to the power minus 2 t by tau divided by minus 2 by tau. This is the constant. 0 to tau minus V square by R tau by 2 into e to the power minus t 2 into t by tau, 0 to tau limit, minus V square by R into putting value of tau equal to RC and divided by 2 under bracket e to the power minus 2 into tau by tau, upper limit minus e to the power 0 lower limit, equals to minus of R will cancel 1 by 2 CV square under bracket 1 by E square minus 1, or 1 by 2 into 1 minus 1 by E square, taking minus inside, 1 minus 1 by E square into CV square answer. Now heat dissipated will be equals to energy stored at t equals to 0 minus energy stored at t equals to tau. So equals to 1 by 2 CV square minus 1 by 2 CV square e to the power minus 2 into t by tau, or 1 by 2 CV square into 1 minus e to the power minus 2 into tau by 2 into tau by tau, equal to 1 by c into V square into 1 minus e to the power minus 2, equals to 1 by 2 into 1 minus 1 by E square into CV square. By evaluating integration I square R dt, so that when a capacitor is charged by connecting it to a battery through a resistor, the energy dissipated as heat equals the energy stored in the capacitor. By evaluating integration I square R dt, so that when a capacitor is charged by connecting to a battery through a resistor, energy dissipated as heat equals the energy stored in the capacitor. We have dh equal to I square R dt. Hence h will be integration of dh integration of I square R dt, or equals to integration of I naught square e to the power minus 2 into t by tau R dt. I naught square R integration e to the power minus 2 into t by tau dt. Or integrating it will I naught square R under bracket e to the power minus 2 into t by tau by minus 2 by tau, or equals to minus I naught square into R into tau by 2 e to the power minus 2 into t by tau, or minus of E square, minus of E square by R into RC by 2 e to the power minus 2 into t by tau, putting tau value of tau, R square by will cancel, also minus 1 by 2 E square C equals to minus 1 by 2 Ce square e to the power minus 2 into T by tau. Negative sign indicates that heat is dissipated. So now EC will be 1 by 2 C into Vc square. The energy stored in the capacitor is given by, or 1 by 2 C, and Vc is given by E into e to the power and T by tau to the whole square. So 1 by 2 C E square e to the power minus 2 into T by tau. So we get the value same like energy dissipated. So energy stored in the capacitor is equal to the energy dissipated by the as heat is equal to energy stored in the capacitor. True. Next, a parallel plate capacitor is filled with a dielectric material having resistivity ρ and dielectric constant K. The capacitor is charged and disconnected from the charging source. The capacitor is slowly discharged through the dielectric so that the time constant of the discharge is independent of all geometrical parameters like the plate area or separation between the plates. Find this time constant. Solution: leakage current. Dielectric is not a perfectly insulating material. So when the space between the plate is completely filled with a dielectric, there flows some charge through the dielectric medium when connected to the battery. The flow of charge per unit time through a dielectric medium is called leakage current. Leakage current. Now if battery is removed after full charging, the capacitor starts discharging due to leakage current. We can say that it becomes a case of discharging of a capacitor in CR circuit. In both cases, resistance of the dielectric is R equals to rho into L by A, or R equal to rho into D by A, because distance will be equal to the capacitor distance. This thus leakage current in circuit I equals to V by R, or V equals to V by rho D by A, or A into V by rho into D. Because potential difference across this is V, and current, leakage current is I. So using the formula, and the resistance is R. Dielectric material is given, so R will be rho into D by A, because this distance is D. In place of L we have used D. So I equal to V by R equal to V by rho D by A, V by rho into D. Similarly, if the capacitor is given a charge Q naught at time t equal to 0, then after time t, Q charge will remain on the capacitor and given by and on it, where Q equals to Q naught e to the power minus T by tau, because this is the case of discharging. So here tau equal to R into C, and R is given by rho into D by A, and C, capacitance of capacitor is, because it is dielectric field, so K epsilon naught A by D. Now A will cancel, D will cancel, so rho into K epsilon naught. So time constant here is rho K epsilon naught. Next question. Find the charge on each of the capacitors 0.2 millisecond after the switch S is closed in the figure. Here it is shown, this is a 25 ohm resistor and it is a 6 volt battery, and these are capacitor in parallel, 2 microfarad and 2 microfarad. This is a switch, and the question is that when switch is closed we have to find the charge on each capacitor. Now we know that C equivalent, because it is in parallel, so C equivalent will be C1 plus C2, 2C or equal to 2 into 2 microfarad equal to 4 microfarad. Again we know that charge is given by Q equal to Q naught 1 minus e to the power minus t by tau, or C equivalent here we will use because we are replacing it with equivalent capacitor. So C equivalent is to E 1 minus e to the power minus t by tau. Now tau will be equal to R into C equivalent. So R is 25 and 4 microfarad equal to 100 microcoulomb. And so it will be C equivalent 4 microfarad into 6 volt or into under bracket 1 minus e to the power minus 0.2 into 10 to the power minus 3 second by 100 microcoulomb, and 24 microcoulomb into 1 minus e to the power minus 0.2 into 10 to the power minus 3 by 100 into 10 to the power minus 6 equal to 24 microcoulomb into 1 minus e to the power 2 into 10 to the power minus 3 divided by 10 to the power minus 3. Okay, safe. True. Or equal to 24 microcoulomb into 1 minus 1 by E square, or 24 microcoulomb into 1 minus 1 minus 0.135, because 1 by E square is 0.135. So equal to 2 microcoulomb into 0.865 equal to 20.76 microcoulomb. Hence charge on each capacitor equals to Q by T equal to 10.38 microcoulomb. Next question. The switch S is shown in the figure is kept closed for a long time and is then opened at a t equal to 0. T equal to 0 it is opened. Find the current in the middle 10 ohm resistor at t equal to 1.0 millisecond. As the switch was closed for a long time, the capacitor is in a steady state, that is the capacitor become fully charged, and so current in circuit, because it is charged in a steady state, so no current will flow through this. So current in the circuit will be from like this, 12 by, it is in series, so 10 plus 10 equal to 12 by 20. 12 by 10 plus 10, 12 by 20 ampere. Now hence PD across capacitor Vc equals to I into R, or 12 by 20 to 10 6 volt. Now when switch is opened, capacitor get discharged, and discharging current is given by I equal to I naught e to the power minus t by tau equals to Vc by R e to the power minus t by tau, or equals to 6 by 10 into e to the power 1 into 10 to the power minus 3 second by 10 into 2 into 25 into 10 to the power minus 6 farad equal to 6 by 10 e to the power minus 10 to the power minus 3 by 25 into 10 to the power minus 5, 6 by 10 into e to the power minus 10 to the power minus 3 into 10 to the power by 25, 6 by 10 into e to the power minus 100 by 20 by 6 by 10 e to the power minus 4, or equals to 6 by 10 into 1 by e to the power 4, or 6 by 10 into, now 1 by e is equal to 0.135, so e square, so multiplying we have 1 by e square is this value. So 0.6 into 0.0182 equivalent to 0.011 ampere, or 11 by 1000 ampere, or equal to 11 10 to the power minus 3 ampere, equal to 11 milliampere. Answer. Next, a capacitor of capacitance 100 microfarad is connected across a battery of EMF 6 volt through a resistance of 20 kilo ohm for 4.0 seconds. The battery is then replaced by a thick wire. What will be the charge on the capacitor 4 seconds after the battery is disconnected? Here the situation is shown, that is a capacitor of 100 microfarad is connected with a battery of 6 volt and with a resistance 20 kilo ohm. And it is connected for 4 seconds. So in the case of charge, this will be the case of charging, because initially the charging Q barabar Q naught into 1 minus e to the power minus t by tau, or C into 1 minus e to the power minus t by tau. Using all this value, we get 6 into 0.865 into 10 to the power minus 4, or 5.190 into 10 to the power minus 4 coulomb after 4 seconds. Now when it is connected to a wire, thick wire of resistance, thick wire, the battery is then replaced. This is replaced by a thick wire. And this charging Q equal to Q naught e to the power minus t by tau, or 5.19 into 10 to the power minus 4 e to the power minus 2. This is a case of discharge, because thick wire does not affect it, because its resistance is equivalent to 0 in compared to this resistance, because this is very high resistance, 20 kilo ohm. So, and it is also a thick wire, and we know that R into rho into R equals to rho L by A. So area is more, the resistance will be less, so its resistance is very less compared to this, so it is considered 0. So we will only consider that capacitor is discharging through this resistance. So Q equal to Q naught e to the power minus t by tau, 5.19 into 10 to the power minus 4 into e to the power minus 2, or solving it, 5.19 into 10 to the power minus 4 into 1 by e square is 0.135, equivalent to 0.70 into 10 to the power minus 4 coulomb, equal to 70 into 10 to the power minus 6 coulomb, yeah, 70 micro coulomb. Answer will be this. This is our answer. Next, question. This is capacitor C1 and C2. This is a switch. It is a battery of EMF resistor. The switch is closed at t equal to 0 when the capacitors are uncharged. Initially it was uncharged. Find the charge on the capacitor C1 as a function of time t. Solution: when switch is closed, capacitor gets charged. As capacitors are in series, charge on both will be equal. Now C equivalent will be C1 into C2 by C1 plus C2. In case of capacitor, equivalent resistance for series is given by this formula. So C equivalent C1 C2 by C1 plus C2, or tau, time constant, tau will be R into C equivalent, or R into C1 C2 by C1 plus C2. Now Q naught will be C equivalent into E, and Q equivalent into E, and Q is given by Q naught into 1 minus e to the power minus t by tau, or E into C equivalent Q naught, E into C equivalent into 1 minus e to the power minus t by R into C equivalent. So this is the formula in terms of time, as a function of time. So this is our formula.